now let's consider the case where something is changing its speed. Something's moving, changing its speed. So that'd be a case of a car here, let's say at rest, so maybe v equals 0, and it accelerates such that at this point v is some value greater than 0. Let's call it, I'm going to call it v1 is greater than 0. Okay. And so that means in order for that to have happened, this must have accelerated during that time period. Okay, so from here to here it accelerated. Well, what does that look like? If the velocity is increasing all the time, what does a position versus time graph look like? Okay, here's our position versus time. Let's go ahead and choose our coordinate system such that it starts at 0 at t equals 0. Okay, well, initially it's really slow. Okay, in fact it starts at 0, so it's coming out barely with any slope. But then it accelerates until it gets to a velocity that's non-zero. Okay, let's say that that's the time over here, and it's got a non-zero slope, something like that. Okay, fairly, if this is a large acceleration. Well, if you keep doing that idea, at a later time, somewhere around here, the car is moving not zero, but slow, but it's got a steeper slope, and then it continues to do that, and the slope continuously changes as it accelerates, as the speed increases. So the slope here is equal to the value here, the slope here is equal to the value here, and any point in between, the slope is equal to the value of the velocity along that line. But the curiosity here is this is changing constantly. So there's no straight lines here. So how do you find the slope of a straight line? Which you may remember is the tangent to a line. So this straight line is tangent to a spot right there. And if I were to be able to zoom into that spot, I'd see that though it's curving, it's pretty straight. And this section right here looks awfully straight. It looks like a straight section with a rise and a run. Okay, and so I could take my definition of velocity is equal to the delta x over the delta t, and if I take my delta x to get smaller and smaller and smaller, which means my delta t is getting smaller and smaller and smaller, I can zoom in to a point on this curve such that it looks pretty darn straight. And that is the idea of calculus. This no longer is just a delta, but it becomes a derivative. But I want to note that a derivative doesn't mean anything fancy beyond it's a difference still. It's just a really, really small difference. Now that offers us all the amazing mathematics of calculus to be able to find certain values, but it's far more important in physics to remember that a derivative is still just a difference over a difference, and it's still equal just to the slope of a line. So with that in mind, we can look at this slope, and though this is now defined as a derivative of position with respect to time, it still is just the slope of that line. And so we call this the instantaneous velocity, because no matter how curvy this is, we can always take our difference to be small enough that we can approximate that section as a straight line.